It's a quiet Friday afternoon in northeastern Japan. The cherry blossoms are just beginning to bloom, and workers at the Fukushima Daiichi nuclear power plant are going about their routine maintenance tasks. 6 massive reactors stand along the Pacific coastline, their cooling systems humming steadily as they generate electricity for millions of homes across the region. Everything appears normal on this March day in 2011. But beneath the ocean floor, approximately 130 kilometers east of the power plant, tectonic forces that have been building for centuries are about to unleash their devastating power. And for the 50 workers who remain on duty at Fukushima Daiichi, a series of catastrophic events is about to unfold that will test every safety system, every backup protocol, and every emergency procedure they have ever trained for. This is the story of how a natural disaster became a nuclear catastrophe that changed the world forever. The Fukushima Daiichi nuclear power plant sits on Japan's eastern coast, a massive industrial complex that has been generating electricity since 1971. The facility houses 6 boiling water reactors, each one a marvel of engineering designed with multiple layers of safety systems. These reactors had operated safely for decades, weathering typhoons, earthquakes, and countless routine shutdowns without incident. The plant's location seemed ideal when construction began in the 1960s. The Pacific Ocean provided an endless supply of cooling water, while the relatively stable coastal terrain offered what engineers believed was a secure foundation. The facility was built to withstand the most severe natural disasters that historical records could predict, with seawalls designed to protect against tsunamis up to 5.7 meters in height. On March 11, 2011, 3 of the 6 reactors are operating at full capacity. Units 1, 2, and 3 are generating a combined 2,381 megawatts of electricity, their uranium fuel rods creating the controlled nuclear reactions that heat water into steam, which then drives massive turbines. Units 4, 5, and 6 are offline for routine maintenance, their fuel rods stored in cooling pools within the reactor buildings. The control rooms are staffed by experienced operators who monitor hundreds of gauges, switches, and computer displays. These men have trained for years to understand every aspect of their reactors, from the complex physics of nuclear fission to the intricate network of pipes, pumps, and valves that keep the systems running safely. They know that nuclear power demands absolute precision and constant vigilance. At 2:46 p.m. local time, the ground begins to shake. But this is not an ordinary earthquake. Deep beneath the Pacific Ocean, a section of the ocean floor measuring 500 kilometers long and 200 kilometers wide suddenly shifts upward by several meters. The North American tectonic plate, which had been locked in place by friction, finally breaks free from the Pacific plate in a violent release of energy that has been accumulating for over 1,000 years. The magnitude 9.0 earthquake that results is the most powerful ever recorded in Japan and among the 5 strongest earthquakes worldwide since modern record-keeping began. The seismic waves race toward the Japanese mainland at speeds of several kilometers per second, carrying energy equivalent to thousands of nuclear weapons. When the shaking reaches Fukushima Daiichi, the control room operators feel the building sway violently from side to side. Emergency alarms begin blaring throughout the facility as automated safety systems detect the dangerous ground motion. Within seconds, control rods are automatically inserted into the 3 operating reactors, immediately stopping the nuclear chain reactions in what's known as an emergency shutdown, or SCRAM. The operators breathe a momentary sigh of relief. The reactors have shut down exactly as designed, and the primary danger of an uncontrolled nuclear reaction has been eliminated. But their relief is short-lived. Even though the reactors are no longer generating power, the uranium fuel rods continue to produce enormous amounts of heat through radioactive decay. This decay heat represents about 7% of the reactor's full power output, and without proper cooling, it's more than enough to cause the fuel to melt. The earthquake has severed the external power lines that normally supply electricity to the plant's cooling systems. But the engineers who designed Fukushima Daiichi anticipated this possibility. Massive diesel generators, located in the basement levels of the reactor buildings, automatically start up to provide backup power. These generators have enough fuel to run the cooling pumps for several days, giving operators time to restore external power or arrange for additional fuel deliveries. For nearly an hour after the earthquake, the backup systems work flawlessly. The diesel generators power the cooling pumps that circulate water through the reactor cores, carrying away the decay heat and preventing the fuel from overheating. The operators focus on assessing damage throughout the facility and coordinating with emergency response teams. They believe they have successfully weathered the worst natural disaster in Japan's modern history. But the earthquake was only the beginning. The massive seafloor displacement has created something far more dangerous than seismic waves. Across hundreds of thousands of square kilometers of ocean, billions of tons of water have been lifted upward and are now racing toward the Japanese coastline in a series of tsunami waves traveling at the speed of a jetliner. At 3:27 p.m., exactly 41 minutes after the earthquake struck, lookouts at Fukushima Daiichi spot a dark line on the horizon. The first tsunami wave is approaching the coast, and it's already clear that this wave is far larger than anything the plant was designed to withstand. The 5.7-meter seawalls that were supposed to protect the facility suddenly seem woefully inadequate. The wave continues to grow as it approaches the shallower coastal waters, drawing energy from the ocean depths and focusing it into a wall of water that towers more than 14 meters above sea level. As it crashes over the seawalls and floods across the plant site, everything changes. The tsunami water pours into the basement levels where the diesel generators are housed, drowning the backup power systems in seawater and plunging the facility into what nuclear engineers call a station blackout. Without electricity to power the cooling pumps, the operators face their worst nightmare. The reactors are shut down, but the fuel rods are still generating deadly amounts of heat, and there's no way to remove that heat from the reactor cores. In the pitch-black control rooms, illuminated only by the pale glow of battery-powered emergency lighting, the operators realize they are facing an unprecedented crisis. The station blackout has eliminated not just their ability to cool the reactors, but also their ability to monitor what's happening inside the reactor cores. Most of their instruments have gone dark, leaving them essentially blind to the conditions where the fuel rods are slowly beginning to overheat. The plant's emergency response team immediately begins implementing their severe accident procedures, protocols that had been developed but never tested under real-world conditions. They know they have only hours before the situation becomes catastrophic. Without cooling water circulation, the temperature inside the reactor vessels will climb steadily upward, and the water level will begin to drop as steam escapes through relief valves. Teams of workers wade through contaminated floodwater in the lower levels of the buildings, desperately trying to restore some form of power to the cooling systems. They drag emergency cables through the darkness, connecting portable generators and batteries in a frantic attempt to get the pumps working again. But the damage from the tsunami is extensive, and many of the electrical systems that weren't destroyed outright have been rendered inoperable by saltwater corrosion. By evening, conditions inside the reactor cores are deteriorating rapidly. The water levels have dropped below the tops of the fuel assemblies in Unit 1, exposing the uranium fuel rods to steam and superheated air. Without the cooling effect of water circulation, the zirconium cladding that surrounds each fuel rod begins to heat up beyond its design limits. As the cladding temperature climbs past 1,200 degrees Celsius, a dangerous chemical reaction begins to occur. The superheated zirconium starts reacting with steam to produce hydrogen gas, a highly explosive substance that begins accumulating inside the reactor containment structures. This hydrogen production not only creates the risk of explosion, but also consumes the limited water remaining in the reactor vessel, accelerating the fuel exposure and heating process. Plant manager Masao Yoshida faces an agonizing decision. The only way to prevent complete fuel melt is to inject seawater into the reactor cores, but doing so will permanently destroy the reactors and contaminate them with salt. Each reactor represents an investment of billions of dollars, and the decision to flood them with seawater essentially means writing off the entire facility. But with no other options available, and the situation growing more desperate by the hour, Yoshida authorizes the unprecedented step of sacrificing the reactors to prevent an even worse disaster. Fire trucks are positioned outside the reactor buildings, their hoses connected to seawater intake points that engineers hastily identify and modify. The first injection of seawater into Unit 1 begins around midnight, more than 9 hours after the tsunami struck. But the operators don't know if they're already too late, or if the makeshift cooling system will be sufficient to prevent a complete meltdown. Throughout the night, small teams of workers venture into the highly radioactive reactor buildings to manually operate valves and monitor conditions. These men, who would later be called the Fukushima 50, expose themselves to dangerous levels of radiation in their attempts to regain control of the situation. They work in shifts measured in minutes rather than hours, racing against time and their own radiation dose limits. At 3:36 a.m. on March 12th, a massive explosion rocks the Unit 1 reactor building. The accumulated hydrogen gas has found an ignition source, creating a blast that blows off the upper portion of the building and sends a cloud of radioactive debris into the atmosphere. The explosion is felt kilometers away and captured on video by news helicopters, providing the world with its first visual evidence of the unfolding nuclear disaster. The explosion destroys much of the equipment that workers had been using to inject water into the reactor core, forcing them to start over with new connections and different injection points. Meanwhile, similar conditions are developing in Units 2 and 3, where the fuel rods are also becoming exposed as water levels continue to drop. On March 14th, Unit 3 suffers its own hydrogen explosion, even more violent than the first. The blast sends debris flying hundreds of meters and creates a massive plume of smoke and steam that rises high into the atmosphere. Television cameras around the world broadcast the explosion live, creating panic among viewers who witness what appears to be a nuclear facility literally blowing apart. But the worst is yet to come. Unit 2, which has been the most challenging reactor to cool throughout the crisis, suffers what engineers believe is an explosion inside the containment structure itself. This explosion doesn't destroy the reactor building like the others, but it potentially breaches the primary containment that's supposed to prevent radioactive material from escaping into the environment. As the crisis enters its 4th day, the situation becomes even more complex. Unit 4, which had been shut down for maintenance, develops its own emergency when the spent fuel pool begins to overheat. This pool, located high in the reactor building, contains hundreds of highly radioactive fuel assemblies that must remain underwater to prevent them from overheating and releasing radiation. With no power to operate the cooling systems for the spent fuel pool, the water temperature begins to rise, and the water level starts to drop through evaporation. If the fuel assemblies become exposed to air, they could ignite spontaneously, creating a massive fire that would spread radioactive contamination across a much wider area than the reactor accidents alone. Military helicopters are deployed to drop water onto the spent fuel pools from above, while ground-based water cannons typically used for riot control are repositioned to spray water into the damaged reactor buildings. These desperate measures represent humanity's attempt to use any available tool to prevent the complete collapse of nuclear containment at Fukushima Daiichi. The radioactive releases from the damaged reactors create an evacuation zone that expands outward from the plant, displacing more than 100,000 residents from their homes and contaminating hundreds of square kilometers of farmland and forest. The invisible threat of radiation transforms the Japanese countryside into a forbidden zone where normal life cannot continue. The disaster at Fukushima Daiichi stands as a stark reminder of how quickly the unthinkable can become reality. What began as a routine Friday afternoon transformed into the world's worst nuclear accident since Chernobyl, not through human error or mechanical failure, but through the awesome power of nature exceeding every assumption engineers had made about the limits of catastrophe. The brave workers who remained at the plant, risking their lives in those first critical days, prevented an even greater disaster through their courage and sacrifice. Their actions saved countless lives and demonstrated the extraordinary lengths to which ordinary people will go when faced with extraordinary circumstances. Today, more than a decade later, the cleanup continues. Advanced robots navigate the ruins of the reactor buildings, and innovative technologies slowly remove the melted fuel that remains locked within the damaged cores. The exclusion zone around the plant has begun to shrink as radiation levels decline, but the full recovery will take generations to complete. The lessons learned from Fukushima have reshaped nuclear safety protocols worldwide. New designs incorporate passive safety systems that don't rely on external power, and existing plants have been retrofitted with additional backup systems and higher seawalls. Yet, the fundamental question remains. In a world where the forces of nature can exceed our wildest predictions, how do we balance our energy needs with the risks we're willing to accept? The story of Fukushima is ultimately a human story, one of ordinary people facing an impossible situation with courage, determination, and an unwavering commitment to protecting others, even at great personal cost.